In this video, we're going to go through the 2023 chemistry practical exam. I know many students are going to get worked up over this, but I think chemistry practical exam cannot get any easier than this. So there were 3 experiments. The first one is a sulfur clog experiment, the second one a qualitative, and then followed by a gravimetric experiment. The first experiment is a sulfur clog experiment, which is related to the chapter of speed of reaction. In a clog experiment, we measure the rate of reaction by recording the time taken for a fixed amount of product to form. And very often, the reaction would produce a colored solid or colored solution. And then we measure the time taken for a fixed amount of that solid to form. So in this experiment, we are measuring the time taken for a fixed amount of sulfur, which is formed from the reaction of sodium thiosulfate, that is your solution B, and hydrochloric acid, which is your solution A. So when you mix A and B, the reaction actually produces a colored solid in the form of sulfur. So over time, after mixing the two reagents, you will find that solid or the solution starts to get a little turbid, meaning a little cloudy. And then we measure the time taken for enough sulfur to form such that we can no longer see the mark that we make on the test tube. In the question, they stated very clearly for you to record timing to the nearest second. I think that is a common mistake that students tend to make, especially if they don't read the question carefully. So for this experiment, we conduct 5 experimental runs, each with a different volume of B, which is your sodium thiosulfate. In all 5 experiments, your hydrochloric acid is in excess. And in a feature of your clog experiment is that in all experimental runs, your total volume of solution must be the same. So in all experimental runs, we make the total volume the same by topping up with deionized water. So the total volume of all 5 experiments, or in each of the 5 experiments, would be 11 centimeter cube. For clog experiments, remember the rate is determined by the time taken for a fixed amount of product to form. And since the amount of product is fixed, is actually a constant, so what we can see from this equation is that rate is inversely proportional to time, meaning the faster the reaction, the shorter the time taken for your sulfur to form. So the other relation that we need to make in this experiment is that the volume of thiosulfate used or volume of B used is related to the concentration of reactant. So the greater the volume of B, the higher the concentration of B, the faster the speed of reaction or the rate of reaction should be. So in your experimental runs, the sequencing of the experiments is a little weird, but I believe there must be a reason for that, because if we were to start with experiment 2, some of y'all may not know that a yellow solid will form and may discard it after like 5 minutes or so. So the designer of this experiment actually placed experiment 1 to indicate to you that, you know, a precipitate or yellow solid will actually form after some time. And then before we go on to the longest experiment, which is experiment 2, where it will take typically between 5 to 6 minutes. So what we can see from experiments 2 to 5 is that when the volume of thiosulfate increases, meaning the concentration of reactants increases, the time taken is actually shorter. So in this particular question, you are required to calculate rate as well. You are given the equation to take 1000 divided by the time, and It's also stated in the question to leave your rate to 3SF. I really hope that all of y'all did remember to do that. So following that, you're supposed to plot a graph of rate against volume of B. As shown in the earlier equation, rate is proportional to, or inversely proportional to time, and rate is actually proportional to concentration of B or volume of B. So if we were to plot 1 over T or 1000 over T, which is your rate, against concentration or volume of B, we will be plotting a y equals to x kind of graph. In fact, the question is very kind to tell you that your line must pass through origin as well. So the thing about clock experiments is that they or especially sulfur clock experiment, is that it's usually not very accurate. A reason being, different people might interpret whether you can see the spot differently, all right? Especially for not so young teachers, where we have the early onset of cataracts, and then plus the perennial lack of sleep. When I was performing the experiment, I found it very, very hard to determine whether the spot was still visible or not. Okay, so more often than not, you may get values that seem anomalous. So the question already advised you that if you have any anomalous spots, to circle them. Otherwise, you can actually plot a best fit line passing through the origin. And again, a best fit line would consist of roughly equal number of points above and below the lines, and the perpendicular distances of the points from the line should roughly cancel out. So in part C, in part B, part 2, you are supposed to find the speed of reaction should 1.7 centimeter cube of B be used. That you can easily find from the graph. So you're supposed to locate x equals to 1.7, and from your line, the line that you have drawn, to find the corresponding y value. That would be the rate at which 1.7 centimeter cube of B was used. In C part 1, you're supposed to calculate the concentration of B in experiment 1. Okay. In part 2, you're supposed to deduce. Initially, when I read the question, I was slightly taken aback as to why is there a need to deduce, because deduce usually is used when we cannot find out exactly what is the value, or there is no means of finding out. But over here, the concentration of B can actually be easily calculated using the same method in part 1. Okay, so let's look at how we calculate the concentration of B in experiment 1 first. So we take the initial concentration of thiosulfate, multiply by the volume used. In experiment 1, we use 10 centimeter cube of thiosulfate divided by the total volume of the mixture, which is 11. So that is how we calculate the concentration of B in experiment 1. Similarly, we can use the same equation to calculate the concentration of B in experiment 2, but given the fact that they ask you to deduce, meaning they don't want you to use the same methods. So based on the word deduce, it means that you need to make use of whatever they've just found and deduce the concentration of B in experiment 2. So over here, the logic is this, that in experiment 2, we are using 2 centimeter cube of B, and that is 5 times or 1 over 5 times of the initial volume in experiment 1. Okay, and since the total volume is the same, so your volume of B is actually proportional, or your concentration of B is actually proportional to the volume of B used. And in this case, since it's 5 times lower, you just need to take your answer in part 1 and divide it by 5 to deduce the concentration of B in experiment 2. For part 3, I would say this is a routine theory question. You're supposed to describe and explain. So be very sensitive to these 2 words. Describing means you just only need to state the relation that you can see, which is that when the concentration of B increases, rate increases. That would give you your 1 mark. Explain. For this question, they want you to explain using the graph as well as using ideas of colliding particles. So that is using collision theory. So you need to explain that concentration of B depends on the is proportional to the volume of B. So therefore, when volume of B increases, concentration also increases, which therefore tell us that when concentration increases, the rate of reaction increases. And how do we explain for that using collision theory? Is that we have more particles per unit volume, therefore frequency of collisions increases, frequency of effective collisions increases. In C part 4, the question is asking for the purpose of adding water in experiments 2 to 5. The reason for that is, as mentioned, an important feature in the clock experiments, which is that the total volume of the solutions in all experimental runs must be kept constant. So I believe that is the first point that we are looking for. The second point is then to explain why must it be kept constant. There are 2 reasons for that. One is so that the amount of sulfur required to be formed to block the spot from view is the same in all experimental runs. So imagine if the total volume of solution is different, then you would take a different amount of sulfur to actually cover the spot. The second reason is for the total volume to be kept constant is so that the concentration of your thiosulfate or concentration of B is then directly proportional to the volume. So when volume increases, we can therefore say that concentration of B increases. In D part 1, you're supposed to calculate the percentage uncertainty of a measurement. For this, we learned that in physics but not in chemistry. In this case, the formula is given to you, so you just need to substitute the correct values into the formula to find that the uncertainty is 2%. And the question goes on in D part 2 to ask you for an experimental modification to the equipment used to improve accuracy. Now, a trick in taking exams is that for D part 2, this is part 2 of D, meaning it must be related to part 1. In part 1, you were asked to calculate the uncertainty related to your measuring cylinder. So it's hinting to you that your measuring cylinder is not accurate. It has a 2% uncertainty. So naturally, if you gather that the answer to part 2 is to use a more accurate apparatus for measuring volume, that is using a burette. The next experiment is our all-time favorite qualitative analysis, and this time it is very, very straightforward. You are given a sample of C. The question already tells you that it contains copper carbonate and another anion. So you have copper carbonate in the solid sample. In test number 1, you are supposed to heat the solid gently followed by strongly. I've mentioned this many times in class. I've mentioned this in the videos as well. When you heat gently, you are trying to remove the water of crystallization, if any. And when you heat strongly, you are trying to cause the solid to decompose into simpler substances. So the fact that you have copper 2 carbonate, you should expect that it will decompose to form copper 2 oxide, which is black, and carbon dioxide gas. So before you even perform the heating, you should prepare your lime water and a delivery tube. So for this experiment, without even doing, you should expect a few things. Number one, the green solid will turn black. Number two, a gas is produced which form a white PPT in lime water. The last one, which is uncertain, which you need to perform the experiment to find out, is whether there's any water of crystallization present in the other copper salt. So if you have performed the heating, you will notice that there are some colorless liquid form at the mouth of the test tube. So that's an indication that there is water of crystallization. So the other copper salt is actually a hydrated copper salt. So once again, for test number one, there are three important observations. Number one, your green solid turned black. Number two, a colorless liquid formed at the mouth of the test tube. Number three, gas produced form a white PPT in lime water. For test number two, you're supposed to add nitric acid into a boiling tube of sample C. Once again, you have a carbonate. You are adding an acid to a carbonate. If you are not going to test for carbon dioxide, I don't know what you're going to test for, or I don't know what you have been studying for the past 2 years. So before you add the acid to your carbonate or carbonate to your acid, get ready your lime water and delivery tube, and as soon as you add the solid to the acid, immediately cap it, and remember you need to shake the boiling tube a little to make sure that the reaction is complete and to force the gas to bubble into your lime water. For this experiment, some of you may not see a white PPT forming in your lime water. The reason for that is that you are using a boiling tube, number one. Number two, the amount of carbon dioxide produced is not a lot. And the thing about using boiling tube is that there is a significant volume of air that's inside the boiling tube before the experiment or before the reaction has taken place. So when you first bubble, you may see a lot of bubbles in your lime water. Those are bubbles of air, not your carbon dioxide. So you need to continuously shake your boiling tube for a long time before you start to push the carbon dioxide into your lime water, and only then your lime water will form a white PPT. For test 3, 4, and 5, this is your standard QA test. Test number 3, aqueous ammonia, is to test for cations. We already know that it's copper, so you will have a blue PPT soluble in excess to give a dark blue solution. 4 and 5, 4 is the test for sulfate. So if you have done it correctly, you shouldn't see any PPT. So that concludes that sulfate is absent. And when you add silver nitrate, that is the test for chloride or iodide, you should see a white PPT. That means that chloride is present. So the other salt that's present in C is actually hydrated copper 2 chloride. So C is a mixture of copper 2 carbonate and hydrated copper 2 chloride. Part B is a gravimetric experiment where we measure the mass of your reaction mixture before and after reaction and make use of the data to calculate the percentage by mass of calcium carbonate in an impure sample. So for this method to work, normally the reaction will produce a gas. The gas would escape from your reaction mixture, leading to a mass loss. And the value of your mass loss would indicate the mass of your gas that was produced. So this question is actually quite straightforward, but unfortunately, I think because of the way that it was phrased or designed, many students actually stumbled on this question. Why? The question requires you to measure two things. Number one, mass of conical flask plus A, which is your acid, and then mass of conical flask and contents when the reaction is complete. So what many students realized or was shocked upon measuring is that the mass of the final mass is actually more than the initial mass. And then they are stumped, they cannot move on from there. So what they fail to realize is that the mass of conical flask Na is not representative of the initial mass, because you still need to add the mass of your solid D. So I don't know whether it was the intention of the setter or just the design of the question wasn't good enough, because all we need to add into the question is for students to record the mass of conical flask Na plus solid D, for students to recognize that that represents the total mass of your reaction mixture before the reaction. So for those of you who recognize that, congratulations. So you need to add 0.7, which is the mass of D. So taking the initial mass minus the final mass, you will get the mass of carbon dioxide. The remaining calculations are very routine. You just need to find the number of moles of carbon dioxide. By comparing mole ratio, you will get the number of moles of copper 2 carbonate. Multiplying by the molar mass, you will get the mass. And then you just take the mass of copper carbonate divided by the mass of D, multiply by 100 to get the mass percent. Now don't worry if you get a value that is different from what I have, because different students or different candidates will get a slightly differing mass of D. Even though we have put down the mass of D as 0.7 in the question, in actual fact, it was a range of masses that was actually measured from 0.65 to 0.75. So each candidate may get a slightly differing mass of D. So that will give you a different percentage mass calculated. That is perfectly fine. The last question is a planning question. So this planning question I think is fairly easy, and even if it's not, the hints given in the question should be clear enough. You are given the boiling points of propanoic acid and propanol. So that is like a big shout to you that you need to separate using the basis of the differing boiling points, and the method that we should be using would be fractional distillation. So you need to be able to draw the setup for fractional distillation, and when you're drawing the setup for fractional distillation, remember there are several important aspects of fractional distillation. For example, you need to add your boiling chips. For example, the position of the thermometer next to the side arm leading to the condenser, and also in the condenser, your tap water must enter from the bottom and exit from the top. For this particular experiment, one important feature that I thought is important, but students may or may not realize, is that your propanol is volatile. Boiling point is 49 degrees Celsius. So when you collect the fraction, when you collect your propanol, your conical flask must be immersed in an ice bath or at least cold water to prevent propanol from evaporating. So the procedure probably goes something like this. You set up the apparatus as shown. You heat the mixture using a Bunsen burner or Bunsen flame, and then you collect the distillate when the temperature shown on the thermometer is constant at 49 degrees Celsius. If I have the time, I would actually explain the procedure. So I would mention something like, the components of the mixtures have different boiling points. So I'll point out the boiling point of propanoic acid. Water is 100 degrees Celsius. Ionic compounds is way higher than that. So propanol, being the liquid with the lowest boiling point, would actually boil first and be collected first. So it's the first fraction to be collected. When I first saw the question, I thought it was slightly unfair, just slightly bit unfair, because students do not learn what is propanol. They may not know that propanol is soluble in water, Reason being, we only learn alcohols and carboxylic acids, and they will have to make the assumption that propanol has similar properties to alcohols and carboxylic acids, meaning the smaller members are actually soluble in water. For students who think that propanol is just a normal organic compound, they may think that it's immiscible, and therefore you may need to use a separating funnel to separate them. But propanol is, it has similar properties to alcohols and carboxylic acids. It falls into the homologous series of carbonyl compounds or aldehydes. So yes, so I think it is slightly unfair. However, it is made up for by the boiling points being stated in the question. The last part of planning requires you to determine the purity of propanol by checking whether any propanoic acid is present. So the question actually requested for a reagent that you can add to test for the presence of propanoic acid, as well as the expected observations. So this is again a fairly straightforward question. The reagent you add must react with acid and produce a visible observation. And visible observations, there are two usual types. Number one would be bubbles, so effervescence. Number two would be a color change. So in this case, to test for an acid, we can simply add a carbonate. Any carbonate will do, and then look out for carbon dioxide gas, or look out for bubbles or effervescence, or you may add a metal and similarly look out for effervescence. So if there is effervescence, it means that your propanoic acid is present. If there are no bubbles, it means that your propanoic acid is absent. So as we have seen, other than the little stumbling block associated with the gravimetric experiment, the rest of the experiments and questions are pretty straightforward and routine. So I hope that many of y'all were able to answer the questions, were able to perform the experiments correctly. Even if you haven't, it's time to focus on your paper 2 and then paper 1. So all the best for your O-level exams.